So based on the previous video, we now have two different ways of approximating the solution to an advection diffusion equation in a finite element space. We can use the Golurkin approximation, the one that we're very familiar with. The problem was that we then get these instabilities, right, these oscillations, and that's why we're considering all these different stabilized methods. But nevertheless, the Golurkin approximation is a valid formulation. And then we have the least squares formulation, where we have this differential operator acting on phi and a differential operator acting on w. Now, both of these formulations have problems. Again, the Galerkin approximation is somewhat unstable. It produces these oscillatory solutions, and we're not happy with that. But the least squares approximation is something that we're typically not really able to do due to that requirement on our spaces of being an H2. We need to be able to take two derivatives. So I think I've done this before, but I would like to re-emphasize why we're not allowed to do that. And I'll make the same drawing as I made before. For our typical finite element methods, we have shape functions that look like this, that are linearly varying piecewise linears on each element. Right? So this will be an element, this is an element, and in each element these are linear functions. In the neighboring element we have another function. In the next element we have also one such function. And also if we use higher order basis functions, it comes down to the same thing. Right, so we might have something like looks like that, something like looks like that, maybe something like looks like that. And then the next one is gonna look like that. So maybe I should draw this one in dots. Right, so we have a base function that looks like this, and then the other one look like that. No. So what happens if I take one derivative? If I take one derivative on the function that I've shown in white here in a straight line, and then this is a positive value here and a negative value here. No, that's fine. That's a function. So this one is going to be a function in L2. Right? I can square this function, integrate it, and there's not going to be any problem. And the fact that this one is in L2 means that this one is in H1. I can do the same thing here, take the derivative. What would I get? I get a function that is going to be piecewise linear. In the beginning it has a negative value, towards the end it has a positive value, and around here it's 0, right? So it goes like something like this. This one starts off being negative, around here it's 0, and towards the end it's positive. So this one is actually going to look like that. So the same thing, this is a discontinuous function. Nevertheless, I'm allowed to square it and integrate it. So this is going to be a function in L2, and that makes this a function in H1. What happens if I take another derivative? Well, we might look at inside of these elements, and then we say, well, we're taking here the derivative of a constant function. Well, that's going to be equal to 0. So you might say, I'm just going to get a function that looks like this. Right? Just going to get a function that's equal to 0 everywhere. However, that does not satisfy the first rule of calculus, and that's going to be this relation between derivatives and integrals. That if I take the function f, that's going to be equal to the integral of its derivative. Right, so if I take the integral of the derivative of this function, let's call this f, and this were to be the derivative, then this is going to be the integral of 0. And if I take the integral of 0, I'm not going to get a function that looks like the one over here. right? So according to that pretty straightforward line of reasoning, this cannot be the derivative of the function. This cannot be, am I seeing this? No. This cannot be the derivative of this function because this statement is not true. So what would be the derivative of this function? Well, it's certainly true that where this guy is equal to is a constant, that's going to be equal to 0. So this is going to be 0 here and 0 here. But clearly there's something funny going on here. I'm going from a positive to a negative value over a 0 width, right? So what happens here is you actually get an infinitely large derivative. So you would get a spike. That's actually going to be a negative spike. It's very difficult to draw here. Let me move this up a little bit. So you get a negative spike, and as you start to decrease that the width over which you're taking the derivative, then that's going to be steeper and steeper and steeper, and that's actually going to be what we call a Dirac delta distribution. Now, Dirac delta distribution is not a regular function. It's not a function in L2, and it really doesn't fit very well in the framework of functional analysis, even though it's actually very important also in the framework of functional analysis, but it doesn't fit in any one of the function spaces that we've talked about so far. So that is something that we're not allowed to do, not in a direct sense. If we want to do something like that, if we want to somehow take second derivatives of this function, then we can. That's I think the main conclusion that I want to make here. If you want to take second derivatives of this function, then that's not going to be equal to 0, because that doesn't satisfy this relation. So you somehow have to take into account some additional contribution on the boundary. That's going to be a pretty big mess, and that's not something we typically want to do. And that's why this formulation, actually, you have second derivatives here and you have second derivatives here, so you would have a multiplication of those two infinite spikes. I'm not even sure if that's something that is theoretically allowed. Yeah, so that's why we're not able to do something like this. And I would say the same thing goes here, right? If we take the derivatives of those functions, and then you get a positive constant here, a negative constant here, but in between there's a jump, so there would be also a Dirac spike over here. We typically draw these Dirac delta distributions simply with arrows. Oh. So this is not a function in L2, and this is also not a function in L2, and typically we don't really know how to deal with these functions. So that's the main problem. That's why I'm not able to use a least square formulation with our regular finite element shape functions. Now, the problem clearly occurs on the boundary. So what I might do is I might want to state this thing exclusively in the volume. Now, if I only make use of these formulations in the element volume, in the element interior, then well, clearly I'm forgetting about certain parts of my domain, and the result would really be that would be an ill-posed problem. I can't only consider certain sections of my domain. This has to hold on my complete domain. But nevertheless, I could forget about the boundaries, and then this would still be true. Now, it would be true, but it would not define my solution, and that makes it ill-posed. But again, nevertheless, it would be true. This guy, this Galerkin approximation, is also something that is true. It does produce a solution. It is well-posed. It was simply not a solution that we're very happy with, right, with these oscillations. But that is something that we can combine. We can combine the well-posedness of our Golurkin approximation with all the good properties of the least square approximation if we restrict this only to the element interiors. And that's how we then end up with a Galerkin / least square formulation. where we take the bilinear form of our standard problem plus now this additional term, which we've shown we can actually write like L phi h, L WH. And that's going to be equal to our standard linear form plus F WH, LW. And that would be a function if, yeah, okay, and this is of course the important part. If we want to do something like this and we want to make use of these shape functions, the one that we've talked about here, then we can only do this if we treat these two terms only in the element interior and then sum over these elements. Yeah, so this problem is now well posed because, well, that was well posedness was already in the original Galerkin approximation. And it's also stable and has all these nice properties of, or it tends towards these nice properties of the Galerkin least squares formulation due to these additional terms. Now, of course, we can have different weightings. We can either tend more towards a Galerkin approximation or more towards a least square formulation. And that difference can be introduced by introducing here a parameter, tau, which has to be the same left and right, such that if tau is equal to 0, then we obtain a Galerkin approximation. And if tau goes to infinity, then we obtain sort of a least squares formulation. And I still have this tilde here, this sort of, because of course we've forgotten about the boundaries. And that would make this actually an ill-posed problem, right? So we don't take this lower one too literally. Yeah, we're more interested in taus that are not 0, but have a mild value, such that we get a Galerkin approximation with some additional stability from the least squares formulation. Now, this can pretty straightforwardly be rewritten. We move this one to the left-hand side. And then we obtain a formulation that looks like this. Right, and this is again our residual-based stabilized term with the residual of the core scale, so the residual of the finite element formulation, the stability parameter, or stabilization parameter tau, and our stability operator L stab being equal to minus the original differential operator of the problem. And I think that's all I wanted to show in this video. So also the Galerkin least squares formulation fits in that general writing of our stabilization methods, residual-based stabilization methods in this form, and where I motivated SUPG from an upwind or streamlined diffusion perspective. This is something that we can motivate directly from the perspective of a least squares formulation. Yeah, and so all these different stabilized methods, they have different perspectives on them, but in the end, of course, they look very, very similar. Okay, thank you for your attention.